my name is Ananya, and in this presentation, I will be describing how the LCPC transform can measure features of the clock drawing test such that we can provide personalized tracking of cognitive decline based on these clock drawings. So the clock drawing test is a common, simple, and cost-effective tool to measure cognitive impairment in people that are suffering from brain trauma or neurodegenerative disease. As you can see in this image, features that indicate cognitive impairment include the shape of the clock, the position of the clock numbers, and the position of the clock hands. So in this presentation, I will give examples of how software measures clock shapes, number placement, and handwriting. To start, let's discuss how the LCPC transform works in the first place. So the first step is that we outline the shape of the clock and define its centroid. In step 2, we will overlay a 360-degree radial grid and identify intersections between the grid lines and the object. Then in step 3, we calculate the distance of each intersection to the centroid. In step 4, we linearize the intersections by summing all of the intersections on the same grid line into one value for that line. In step 5, we apply the fast Fourier transform, which results in a frequency plot. This plot is a multidimensional representation of the shape that was drawn in step 1. And then finally, in step 6, we can create a scalar rep value to represent the shape in step 1 by creating an index from the values in the frequency plot. Normal clocks drawn by healthy individuals have a nearly perfect circular shape. Dementia, however, can cause people to draw odd clock shapes, such as those seen in the bottom right of the slide. So our first theme are clock shapes that progressively become more like pyramids. The middle column shows the frequency plots of the shapes that exhibit higher values the more the clock becomes squished horizontally. The value in bins 2 through 7 serve as good candidates for creating indices representing these shape differences. At the upper right is an index derived from calculating the median value of bins 2 through 7. At the bottom right is an index derived from the maximum value within bins 2 through 7. Both indices show an increase as the circular clock becomes more pyramid-like. The second theme is left-leaning and right-leaning clocks. The same two indices from bins 2 through 7 shown in linear increasing effect or a threshold effect as the shapes progress from versions 1 to 3. Then the next theme is squared clocks. So the most normal out of these three would be square number 3 at the bottom, since it is radially symmetric like a circle. On the right, you can see that the two indices reflect the deviation of squares 1 and 2 away from square 3. And then our last and final theme is elliptical clock shapes that either lean to the left or lean to the right. These two series are not progressions, so we don't expect the graphs to actually show trends. So when comparing these shapes picked from each of the 6 themes, we see that the index derived from the max value in bins 2 through 7 is capturing the lack of radial symmetry. Among these shapes, pyramid 1 is the most normal since it most closely resembles a normal circle. The value of this index increases dramatically when measured in shapes that lack radial symmetry, such as left lean 1, as well as the 2 ellipses. The clock shapes discussed so far are all but samplings of all possible clock shapes that can result from a patient who is at various stages of dementia. My point is that LCPC Transform can measure precise shapes in ways that ARIA can't actually do very well. While ARIA might provide noisy data, our software produces very clean data. So moving on to the topic of how numbers are placed on clock drawings, we see here that the normal drawing of a clock shows even placement of integers ranging 1 through 12, but dementia causes the bunching of numbers, or writing more than 12 numbers, or even writing no numbers at all. So here we created a series of clocks that have number placements that span one or more of the 4 quadrants, which we refer to as quarters of the circle. So at the bottom is the normal placement of numbers. And then these figures, we remove the outline of the clock because we want to be able to measure number placement independently of clock shape. In the graph on the right, you can see that as the number patterns deviate more from the normal, the index value drops. In this case, we derived an index by summing all the bins in a frequency plot. Interestingly, the clock called 4 quarters has a higher index value than the normal clock, as can be seen with the dotted box. This is because numbers 7 through 11 in the clock, called 4 quarters, are bunched close together, as can be seen in the other dotted box. So lastly, we'll be discussing the shape of handwritten digits. On the left is a normally written number 8. However, dementia can cause patients to draw figures that have some or no resemblance to the normal number. In each case, we can measure the shape of handwritten digits in a way that is personalized for each patient. Each person writes letters with distinct characteristics, but this is not a problem for our software. So I won't go into much detail about how we can measure handwritten letter shapes since we have a separate video that goes into those details. Suffice it to say, our software sees each of these lowercase cursive L's distinctly, and it can do so for each number on a clock. So for those who are interested in how our software measures differences in handwriting, you can see this video on the use cases page of brainscanology.com. In summary, our software is great for objectively measuring clock features in the clock drawing test. We will create a score report that contains a shape score, a number placement score, and a handwriting score. We'll also include scores explaining whether the correct numbers were written and whether the clock hands were drawn correctly. The advantages of our software is that we can provide personalized tracking on a monthly basis. Clock drawing tests can be done from the comfort of the patient's home and require only a pencil, paper, and smartphone camera. Our score reports are objective and quantitative, allowing us to graph a patient's performance over time. This will be helpful to psychiatrists, psychologists, and the patient's caretakers.